So, Hess's law. Hess's law states that the enthalpy change of a physical or chemical process will depend only on the start conditions and the end conditions, or the reactants and the products. It does not matter the path that you take to get to those products. If you do the direct step or a reaction path that requires a few different steps, the change in enthalpy will result in always the same overall value. The enthalpy change is independent of the pathway and the number of intermediate steps. So, for a chemical change, you could have several different steps or a direct path like I stated before. In this example, carbon and oxygen could combine to create carbon dioxide in a few different ways. The first would be just the direct route, where negative 393 kilojoules per mole is given off, meaning it's an exothermic reaction. Or you could have a less direct route where the diatomic oxygen breaks into radical oxygen, 2 moles of radical oxygen, by adding 498 kilojoules per mole in an endothermic reaction as a reactant. Then, since that radical oxygen is so unstable, reacts quickly with a huge release of energy to form carbon dioxide. Negative 891 kilojoules per mole would be the enthalpy change of this reaction, leaving a net result that is exact same as the direct route. So you could have this done in 3 steps, 5 steps, 8 steps. If you're starting with just carbon and oxygen and arriving with just gaseous carbon dioxide, that will always be the change in enthalpy. So we can predict the change in enthalpy using Hess's law by using the molar enthalpies measured in different experiments. If you have 2 or more equations that you have known values, then you can add those equations together to form your target equation. We have a couple of examples of this coming up. When you're rearranging some of these known values, there are 2 things you need to remember. The first being is if you're using the reverse reaction, then you need to multiply your enthalpy value by -1. This means that if it's a forward endothermic reaction, the reverse is clearly exothermic, so you need that value to reflect that. Second, if you're multiplying any of the values in your reaction or dividing by a certain coefficient, you also do the same for the delta H value. So we'll go through an example here. Here we have elemental sulfur combining with diatomic oxygen to create sulfur trioxide. This first equation here is our target equation. The other 2 equations are our known values. We know that elemental sulfur and oxygen to form sulfur dioxide has a negative enthalpy of 320.5 kilojoules, and that if sulfur dioxide reacts with another oxygen molecule, the formation of sulfur trioxide is also an exothermic reaction, releasing 150.4 kilojoules of energy. We can manipulate these equations to arrive at our target equation, meaning we want to have the same number of reactants and the same number of products as our target equation, and we can eliminate any intermediates or catalysts that appear in this reaction. The first thing we're going to do here, since we have 2 moles of sulfur in our target equation, let's multiply this first equation by 2. You'll see that after doing this, we actually arrive at our final example. So, multiplying that value by 2, you need to also multiply the enthalpy change, and then you'll see here that in the first of our known equations, the 2 moles of sulfur dioxide that form would then be used up in our second equation. These can eliminate themselves. These are called reaction intermediates. With that now, you can total up the reactions on each side, and since the first step took 2 oxygen molecules and our second step took 1, our total reactants are 3 oxygen molecules and the 2 sulfur molecules from our first reaction, and our only products are the 2 sulfur trioxide molecules. When you add those 2 enthalpy changes together, you get that negative 791.4 kilojoules is our total enthalpy of the reaction for our target equation. Note that here the unit is kilojoules because we're not looking at molar enthalpy. The difference here would be half, because in our reaction that we had 2 moles of the sulfur versus 1. Divide that number by 2 and you could see that negative 395.7 kilojoules per mole would be the enthalpy change of sulfur into the formation of sulfur trioxide. A second example here, we have a combustion reaction of methane. We know methane with oxygen would form in a complete combustion reaction just the products of carbon dioxide and water, and we know that carbon monoxide would give off an exothermic reaction when combined with oxygen to form carbon dioxide. So those are our 2 known values, and our target equation, because here it's carbon monoxide, we have an incomplete combustion reaction that we want to calculate the enthalpy change. So the first step here, I would say, is you note that you need 2 moles of methane in your final reaction, so let's multiply that first reaction by 2 so that our methane has the right molar value, or sorry, the right coefficient in front of that reactant. And then the next step in this case is, since carbon monoxide is a product in our target equation, but a reactant in our second equation here, we're going to flip the equation so that we have the reverse, so that we have carbon dioxide breaking down into carbon monoxide and oxygen gas. When we do that, you need to remember to flip the enthalpy by multiplying it by -1. The synthesis reaction is an exothermic reaction releasing 566 kilojoules of energy, but the decomposition is the reverse. It's endothermic. It needs 566 kilojoules to enter that system for it to occur. Once you do that, you can total up all the different values. Notice here that in our first known equation, we had 4 moles of oxygen gas, and then 1 more mole is formed as a product in our second equation, meaning that our total reactants is 3 moles of oxygen gas and we have no products. That leaves us with our exact target equation. By adding those 2 enthalpy values together, you get that the delta H of the reaction given is negative 1,214 kilojoules. This concept we're going to talk about in this video is the standard enthalpy of formation. So what the standard enthalpy of formation is a constant value associated with the formation of 1 mole of a substance from its elements at SATP. What that means is, for example, something like methanol here, you would take carbon, a half mole essentially of oxygen, and 2 moles of hydrogen gas to form methanol. All of those reactants are in their standard state at SATP. Elemental carbon, and then diatomic oxygen and hydrogen from its individual element form. If you looked at a metal, you'd have just the solid aluminum forming with a gas, and whatever that is always calculated from its form at the standard state. So how it exists essentially at room temperature. In both of these examples, you are using the half oxygen, which I always frown upon, but it's the standard enthalpy of formation measured in kilojoules per mole. So you need that molar value balanced, so that instead of forming 2 moles of methanol by multiplying each reactant by 2, you form 1 mole of methanol and get negative 239.1 kilojoules per mole as that forms. So all of these are constants that are calculated for the molecules. Notice the state of methanol here is as a liquid. If you had a gaseous methanol, then you would have a different standard enthalpy of formation. Where this applies is water. When you're doing calculations, always be careful for liquid or gaseous water, whichever you are using in your reaction. The equation shown here is a summation equation. So if you don't know, this is a summation. It means the total of all the standard enthalpies of formation of the products subtracted by the total summation of all the standard enthalpies of the reactants will give you the total enthalpy of the reaction. N is the number of moles for each equation, so you need to multiply that molar value by your products and reactants depending on how your equation is written. So let's do an example. This is a third way of calculating standard enthalpies of formation. You can find all of these in a table in your textbook. You could Google these values and get a table of standard enthalpies of formation for common molecules that are being used. This uses Hess's law for the formation. Since you would be forming all of the molecules in a reaction from its standard states, then all your reactants and products would cancel out to arrive at essentially your target equation. The example here that you're looking at is the formation of hydrogen and carbon monoxide gas from water and graphite, where you could calculate those values by adding waters, carbons, and hydrogens together to get the delta H of the reaction. Here we have the equation, and we have the formation of gaseous water from elemental hydrogen and oxygen as a negative 241.8 kilojoule per mole value. Graphite is in standard state, so it would have 0 for its standard molar enthalpy of formation. The products here, the carbon monoxide, since that is a compound, you can look this up and you get this value from the table being negative 110.5 kilojoules per mole, and hydrogen being diatomic hydrogen is in its standard state at SATP, so again it is 0. Total those values together and you get that the total enthalpy of the reaction is 131.3 kilojoules. Here's a second example. You're going to do a lot of calculations with combustion reactions. So it says calculate the heat of combustion of methanol. You can do this by looking up the table or the molar enthalpy information from a table of methanol, oxygen, carbon dioxide, and gaseous water vapor. So there's our equation. Notice here we are multiplying the values by the molar coefficients in the question. Negative 393.5 is the standard enthalpy of formation of carbon dioxide. It's multiplied by 2 because there's the molar value of 2 in the equation. Negative 241.8 is water vapor multiplied by 4. Together you would total these up for the products and do the same for the reactants. Diatomic oxygen is in its standard state and thus it's 0 at SATP. Those are our subtotals for the products and the reactants, meaning the delta H of this reaction is negative 1,275.8 kilojoules. Notice here you may want, because of the delta H naught of combustion, the molar enthalpy of combustion, divide that value by 2, since we have written in the question 2 moles of methanol are combusting, means per mole of methanol, negative 637.9 kilojoules are released.